Hello and welcome to our live coverage of the Lunar and Planetary Science Conference press conference about 2014 MU69. I am your host, Dr. Pamela Gay, and we are here to put science in your brain. Now, if you tuned in expecting the Daily Space, our normal episode of the Daily Space will be following this press conference. Things do tend to often run a little bit behind from LPSC, so we're just waiting for them to start the stream. So feel free to go ahead, ask questions, anything else while we wait. I am just in the process of finding the correct screen on my computer. It is a Monday of science. The Lunar and Planetary Sciences Conference is my favorite conference of the year. Now, it isn't just because this is a conference with infinite coffee, which it is. It's also because this is a conference where many of the missions take the time to, present all of their newest and their best results in longer formats that really allow you to learn about what's going on. The format for the Lunar and Planetary Science Conference is multi-hour long sessions that start out with 20 to 40-minute talks when they combine multiple talks together that focus in on specific subjects. Here we go. Their audio is horrible.
Introduced on the panel is Alan Stern. He's the New Horizons Principal Investigator from Southwest Research Institute. Carly Howard, New Horizons Science Team member from Southwest Research Institute. Sylvia Protopapa, also from Southwest Research Institute. Kirby Runyon from the Johns Hopkins Applied Physics Laboratory. And Bill McKinnon from Washington University in St. Louis. So each of the team members will go over a short presentation to show what they've learned, and then we'll take some questions. And then we also have a very short video to wrap up. So, Alan?
Okay, thank you, Mike. Glad you could all be here with us today. This exploration that New Horizons has undertaken in our extended mission is very fresh, very recent. The flyby that we're going to be telling you about just took place on January 1st, so only about 80 days ago. Most of the data from the flyby is still on the spacecraft, but the data that we already have on the ground is just mouthwatering, and it's really changing our ideas considerably about how the small bodies of the Kuiper Belt, the building blocks of planets like Pluto, were formed. And we're going to show you some of those details. So let me start, not with my name slide, but with this little cartoon view of our now 13-year journey from down near the sun when we launched at 1 astronomical unit here at the Earth, out past the Jupiter gravity assist flyby, and then onward across the great gulf of the middle zone of our solar system where the giant planets orbit, into the Kuiper Belt, the so-called third zone of our solar system. This is, from a scientific standpoint, just an absolute treasure trove of information, that is the Kuiper Belt, about the conditions at the birth era of the planets. Part of the reason that the Kuiper Belt is so valuable is because it's far from the sun, it's very cold, and that helps preserve information about the structure and the chemistry of objects that are out there. But additionally, because the Kuiper Belt is so vast, the populations are very dilute. Even though there are large numbers of things out there, they are very far between each other. And that changes the collisional environment. And that also helps preserve the original information that these bodies have to tell us about. The first step for New Horizons in exploring the Kuiper Belt was to be the first spacecraft to reconnoiter the Pluto system. Pluto is the largest dwarf planet in the Kuiper Belt, surrounded by 5 satellites. And after we completed that task, we proposed to NASA, and NASA accepted a proposal for an extended mission, which had actually been recommended by the Planetary Decadal Survey that Mike Belton chaired, to go on and then to study these building block objects out of which the dwarf planets like Pluto were made. So we used the Hubble Space Telescope to select a target, and then fired our engines in late 2015, just about 3 months after the Pluto flyby, to direct the spacecraft to intercept that object on the auspicious date of 1 January 2019. That object is called 2014 MU69, and it's been nicknamed Ultima Thule, which means beyond the farthest frontiers, which is quite apt, I think. I'm going to show you a video of the approach and then departure to Ultima Thule that John Spencer, who's in this room and can raise his hand, led the development of, and which we will show you later also has an audio soundtrack that Queen guitarist Brian May put together for us. So we'll show you that later. There's Ultima Thule faintly moving against the star fields and growing brighter and moving apparently more and more rapidly as the spacecraft approached it. And then we resolve it and fly right up to this amazing object on New Year's Eve and New Year's Day. And flew past it in the faint light of the Kuiper Belt at a speed of 32,000 miles an hour, passed it at about the range equivalent to Los Angeles to Washington, D.C. And the data sets that we collected are just spectacular. Everything about the flyby, everything we had hoped for actually worked. We spent 2.5 years planning this flyby in intricate detail, everything from how to avoid potential hazards to backup plans. We had 2 full flybys that we designed, one close and one far. We didn't have to use the far one because there were no hazards in our route. And we choreographed a series of several dozen close observations using all 7 scientific instruments aboard New Horizons. And most of the data that we're going to show you was taken in a very narrow slice of time of about 2 hours, just before and after this closest approach. So let me introduce you to Ultima Thule. It is quite a spectacular object. It is a relic of the formation days of our solar system 4.5 billion years ago. As you can see, it looks rather like 2 things stuck together because that's exactly what it is. It is a contact binary, meaning it's a binary pair that used to orbit each other who evolved from a dynamic standpoint, that the orbit shrank and shrank until they merged. And you can see they merged pretty gently. You don't see any signs of violence. And you don't see, for example, stress fractures on the object. And we're looking at something pretty big here. It's 35 kilometers or about 20 miles from tip to tip. If you're familiar with the comet that Rosetta orbited, it would fit very nicely in that large depression on the smaller lobe of the contact binary. This is really remarkable in that we have never seen a pristine contact binary like this anywhere in the solar system. We have seen bilobed comets, but we were never sure when we studied those whether we were looking at something that evolved to that shape or was born with that shape. And yet theoretical models of planetesimal and planet formation predicted that objects like this should be out there. And the very first Kuiper Belt planetesimal that we visit turns out to be one of them. How's that for, you can't get luckier than that, unless they're very common. And that's one of the primary questions that this has raised, is whether these contact binaries, which we could only really tell by going up close, actually turn out to be routine rather than rare. Okay, a little bit of terminology. We'll be using this terminology throughout this press event. You know, we named this object Ultima Thule with a naming contest about a year ago. And then when we found out that it was really 2 objects, that it was bilobate, and being a little bit tired from the 24-hour shifts that we were running, we didn't have very much imagination, so we just split it up. The big lobe is Ultima, and the little lobe gets to be Thule. And we'll also be referring to this bright annulus at the interface between the 2 objects. which we call a neck or a collar. Now I want to talk about two aspects of the science that's coming out of this, and then my colleagues to my right will tell you quite a bit more. But one aspect that I want to talk about are the strange and wondrous albedo markings, meaning reflectivity markings on the surface. Now, everything you're looking at here is unreflective, with an average albedo or reflectivity of only about 7%. And even the bright markings that you see are only about twice that reflective. So in the image processing, we've actually exaggerated that so you can more easily see the bright markings. But keep in mind that everything on the surface of Ultima Thule is dark, and as you'll soon find out, also red. But I'll leave that to my colleagues to show you the color stuff. There are three types of these bright markings, and they're all enigmatic. First, there are many white, roughly circular or oval features of varying sizes. There are more little ones than big ones, and that's probably a hint as to what causes them. Within the science team, we're still working on that. It's possible that many of them are craters that we're just seeing in high sunlight. The second type of features that we see on the surface that are bright markings are these curvilinear features, or lineaments. And you see the collar is probably the poster child for that, but there are quite a number of other ones. And if I can get the laser, I can show you this circular one that's been nicknamed the Road to Nowhere because it just goes around and around. And here are others down here across the surface on the other lobe on Thule, and there are more. And then third, we have bright patches like these two on Thule, and then others that we see on the larger lobe, Ultima, which is a third and different type of bright feature. Also corresponding to this, there are some dark markings as well. But I want to turn to the other topic that I'm going to introduce here, and that is the strange shape of this object. I know that many of you have seen many small bodies in the solar system, comets and asteroids, for example. You've never seen anything like this before, although, as I said a little earlier, the bilobate comets may remind you of it. But this object is actually very flattened, and that caught us by surprise. We did not expect it. You can see in this pair of images as it rotates back and forth some evidence of that. I think we can do it even better by showing you this model. And we have another model down there. You'll notice they're a little bit different, and that's because the shape models are evolving with time as we get more and more data to the ground and can add it into the mix that we're using computers to fit the three-dimensional shape to. So as we approached the object, we saw it something like this, and then as we flew past it, we were able to catch it at a greater angle, and therefore be able to see its three-dimensional shape. And then we even caught it from behind after the closest approach of the flyby. But it's a mystery to us how this object formed. Bill McKinnon, all the way to my right, is going to speculate on that. I want you to notice some interesting aspects of it. Not only are the two lobes both flattened, one is flattened more than the other. They almost certainly formed in the same location. And we know this because otherwise they would have collided at a higher speed had their orbits been very different. And secondly, notice that they are aligned with one another, that they're not twisted, for example, and perpendicular to one another. One's not sitting up on top of the other. So Bill will talk to you about what we call their principal axes and their alignment and what that has to tell us about how they came to be this way together as a contact binary. And with that, I'm going to turn it over to Carly, who's going to talk about color.
I'd rather have the clicker.
You can have that too.
Thank you. Okay, thanks, Alan. Okay, so just a reminder, this was our previous color view of MU69. It had a resolution of about 1.5 kilometers per pixel, and this was released at a press conference back in all the way back on the 2nd of January 2019. And so now we have the highest spatial resolution color observation that was made by the spacecraft. So this isn't just the highest one on the ground, it's also the highest one that we took. And I want to emphasize that this isn't true color. If you were sitting on if you're sitting on New Horizons, this wouldn't be how you would see Ultima Thule. This is enhanced color, so we're going a little bit more into the near IR than your eyes would be able to see. But the theme that goes throughout color is that it is red. So it would look red to your eye, but it wouldn't look quite like this. So this is now morphing into our new color image. So the resolution is about 0.3 kilometers per pixel, and it was taken about 15 minutes before closest approach, from a distance of about 17,000 kilometers. And you can see that the gross color is about the same. That's not surprising. That the two lobes have a very similar color, and that was something that we already knew. But this high resolution image gives us a chance to really dig into what the color variations are across the surface, look at those subtle color variations. And so the first way we're going to do this is by comparing the color of MU69 to the geology. And so that's done here. The left-hand image is showing you that have been stacked together and processed to make this final image. And then the right-hand side shows you what it would look like if you took the MVIC image and you basically colorized the lorry. So we've overlaid that lorry image. And this gives us a first way of looking at how the color corresponds to geology. And you can see that there are, even in this simple enhanced color composite, you can see there are some obvious things. The neck region is not only bright, it has a different color, it's less red. And the same with those bright eye patches, they look like they have a different color too. But it's by making higher order data products that we can really start digging into the subtle variations. And that's what this next slide aims to show you. So there are two products here. The left-hand side is showing you a near IR over blue ratio map. And so you could think of that as kind of a spectral slope. Now, again, I know I've gone from blue to red, but all the time, keep in your mind, this is red. So the blue here is red, and the red here is kind of ultra red. So don't get too fooled by my color scheme. And on the right-hand side, this is that same MVIC image, but now I've tweaked not only the color range, so it's enhanced in terms of the spectral range we're looking at, but I've also tweaked the contrast. And so this is really now deviating from what you would see, but it allows us to bring out some of the subtle color features that we can see on Ultima Thule. And so by looking at these two slopes, these two images, we can start really seeing some of the things, those subtle color variations. So some of the things that jumps out at you, of course, are the neck, and there's a blue spot highlighted here by that bluer spot panel, which shows two very least red regions. And then there's this lineation feature, this sort of blue stripe that's clearly connected with geology. If we move on to sort of what's the most red on this spectrum, you can see that the rim around that informally named Marilyn crater is very red. And there's also a red spot if you look down at the bottom of Ultima. There's a red spot at the bottom. And this is quite interesting because there's actually two spots you can sort of see that have been nicknamed the thumbprints. That bluer spot region up near the neck, and then one further down, that red spot region. And it looks like the geology is very similar, but the color is very different. So maybe that's pointing towards a compositional difference. If we now compare the color of MU69 to other targets in the solar system, that's what you're seeing here. So spectral slope is across the bottom, and spectral slope is really just the gradient as the color moves from blue to red. So the higher the spectral slope, the more red an observation is. So on the left-hand side, we have neutral, and then it goes all the way into the ultra-red. And you can see from the MU69 histogram of its spectral slopes, MU69 is incredibly red, from very red to ultra-red, if we want to use some of the terminology that's often correlated with these spectral slopes. If we compare that to the Pluto system, it sits sort of squarely between Sputnik Planitia, which is a very neutral color, and red Cthulhu. But what's really interesting here, I think, is that it sits almost squarely in the cold classical Kuiper belt distribution. And that's really important because it's telling us that the cold classical Kuiper belt object that we visited is very similar. It has the same sort of properties that we expect to see across that population. So conclusions that we draw about MU69 are maybe applicable to other Kuiper belt objects. This is the first time such an ultra-red object, has been resolved beyond a point source. And so this is a particularly exciting result. You can see that it sits between the neutral and the red centaur populations, and it's a lot more red than objects that we see in our inner solar system, like comets and asteroids. And this isn't perhaps surprising, because we think that the redness of Ultima Thule has been caused by the modification of organics. So organics happen throughout the solar system, sunlight comes in and it changes the structure of those organics, and they turn more red. This is making something that's often dubbed tholins. And unless there's a disruptive process, that reddening, that process kind of continues throughout its lifetime. But comets and other things that come into the inner solar system have thermal processes that happen, and that can disrupt this reddening process. And so the color of Ultima Thule is actually kind of consistent with this idea that we're looking at a primordial object that hasn't undergone any sort of thermal processing or otherwise surface being processed. And with that, I'll hand over to Sylvia.
Thank you, Carly. So the other instrument on board of New Horizons that has been designed to map the composition of each flyby target is LISA. LISA produces spectral maps in the infrared wavelength range from 1.25 to 2.5 micron. This wavelength range is proven to be the most diagnostic for the characterization of objects in the third zone of the solar system beyond the orbit of Neptune. This is because several ices, such as methane, water, present strong absorption features in this region. The New Horizons spacecraft has scanned the LISA instrument across the surface of Ultima Thule several times during approach and on closest approach date of January 1st, 2019. Here I'm going to present one scan in particular, obtained a few minutes prior to New Year's Day at a range of 31,200 kilometers from Ultima Thule. The resulting spatial scale is 1.9 kilometer per pixel. The image on the right-hand side is an image of Ultima Thule as seen from LISA. This image was obtained by averaging the wavelengths between 1.2 and 2.4 micron. Each pixel corresponds to a spectrum, meaning that we are capable of assessing the composition of the target at each pixel. The image on the right-hand side, shown in the previous slide, is placed here side by side with an NVIC color image of the target acquired 15 minutes prior to the LISA measurements at a spatial resolution of 0.9 kilometer per pixel. The NVIC color image has been overlaid on the panchromatic image of Ultima Thule obtained with LORRI. In spite of the lower spatial resolution of the LISA image, there are evidence for distinct regional signatures across the surface of Mu69. It is possible to observe the neck, the bright neck between the two lobes, as well as the large depression on Thule, informally referred to as Maryland. The panel on the right-hand side shows a grand average spectrum of Mu69, obtained combining the NVIC color images in the visible wavelength range, shown here in orange, and the infrared wavelength range spectrum obtained with LISA, displayed instead in white. A clear signature is the red slope from 0.4 to 1.3 micron, as well as absorptions at 1.5 and 2.0 micron, and an absorption at 2.27 micron. In magenta, the dashed line shows a model of the Centaur Pholus published by Cruikshank et al. 1998. So as you can see from this comparison, the spectrum of Ultima Thule strikingly resembles the spectrum of Pholus. We will use the model of Pholus to guide our interpretation of the spectral signatures. To reproduce the red slope from 0.4 to 1.3 micron, a material rich in carbon compounds is required. An example are tholins, which are refractory residues obtained from the irradiation of ices and gases containing hydrocarbons. The broad absorptions at 1.5 and 2.0 micron are tentatively attributed to water ice. The feature at 2.27 micron instead is well matched in shape and position by methanol. Methanol is a small molecule which is obtained readily after oxidation of methane. So this is indicative of the primitive chemical nature of the surface of this target. Additionally, we can say that methanol is a plausible compound on the surface of this target because it's been observed in gas phase in several comets, as well as in solid phase in the dense cloud material toward the protostars. So in conclusion, we attribute the surface of Ultima Thule as characterized by the presence of organic compounds, water ice, and methanol. And with this, I will leave the word to Kirby. Thank you.
Thank you, Sylvia. So I'd like to talk to you about some of the geology that we've been mapping on this small world. Now, this is a small world with, as Alan said, mouth-watering geology, and we're no stranger to small worlds with mouth-watering geology. For instance, the Rosetta spacecraft reconnoitered Comet 67P beginning in 2014. And here, Comet 67P is shown to scale to Ultima Thule, and it's really tiny. On the right, we have a geomorphological map of Ultima Thule, led by Oliver White. And a geomorphological map is where we group terrains of similar patterns and landforms together to try to understand the spatial relationships between different features on there. I'd like to especially draw your attention to the rolling hills on here, the area mapped with M, beginning in M. To me, these small lumps clumped together are reminiscent of monkey bread, where you have lumps of dough that get stuck together, and just like Ultima Thule, they come together to form something wonderful. And there's the label. If we zoom in on some of the other geologic features, a few of the features we see are troughs and craters. Now, craters can be formed in at least 3 different ways. The word crater just means a round, basically round depression, and you can get that 3 ways. Of course, the most familiar way to get a crater is from an impact, from something small hitting something larger, typically. Out here in the Kuiper Belt, over 1 billion miles beyond Pluto, impact speeds are relatively slow. They tend to be a gentle 700 miles per hour or so, and you compare that to around 50,000 miles per hour for the inner solar system. So quite a bit slower, yet you can still form craters. We draw our attention to the informally named Maryland crater on the 3D printed shape model. It's here. Maryland crater dominates the landscape on the Thule lobe. And to us on the geology team, it's been reminiscent of the crater Stickney on Mars's largest moon, Phobos. Typically on solar system worlds, it's not uncommon to have a crater that's large compared to the size of the body, where it tends to dominate the landscape, and that's certainly the case on Ultima Thule. Now, another way you can form craters is not with impacts necessarily, but from being related to troughs, tectonic features. Now, these troughs here on this image are probably related to the monkey bread terrain, the rolling hills, and maybe some tectonic features where there's been extension. A few of these features that are reminiscent of pit craters, as we call them, are 3 in a row here. And this is similar to features that we see not just on Phobos, but on other planets, other worlds. For instance, here in Iceland, we have a series of normal faults with pits in between them. And these form when you have subterranean cracks opening up, and surface material can drain from the surface down into them, forming something that is crater. It's a crater, but it's not an impact crater. The third way I'm going to talk about that we know how to form craters is from sublimation pits. Ultima Thule probably started with a large reservoir of supervolatiles, things like carbon monoxide, nitrogen, possibly even oxygen. These are things that really don't want to be solids. And if they start off as solids, if they experience any warming, they're going to sublimate, turn directly into a gas. And when that happens, they can pop up some of the terrain, exploding out and forming a pit crater. Of course, there's hills and streaks across Ultima Thule. Again, the monkey bread terrain. Bill's going to be talking more about the original assemblage of Ultima Thule that's hinted at by terrains like this. But the hills, of course, create gravitational gradients, the hills, where things can slide downhill. And there's light streaks across this small world. For instance, in Maryland Crater, there's a number of bright streaks that could be related to basically low gravity avalanches. Even though the gravity of Ultima Thule is around 1 millimeter per second squared, or 1/10,000th the gravity of Earth, things still fall downhill. And the bright features, including the bright neck or collar region, which is also in a gravitational low, it's in a valley, could be areas where we have finer grained material that has slid downhill, brightening the surface. Finally, this animation, which, by the way, is only composed of 2 actual spacecraft images, and their intervening frames have been tweened together or interpolated. This was posted to unmannedspaceflight.com by citizen scientist Roman Kachenko, and we're grateful that he made this public. But this shows the change in perspective as the spacecraft came to its near closest approach with Ultima Thule. And one thing that I think becomes apparent in this is kind of the bent neck that may be indicative of how these 2 lobes slowly orbiting each other came together and slowly collided at the speed you might run into the wall to form this bilobate object. And on that note, I'd like to pass the clicker off to Bill.
Okay, thank you very much, Kirby. Okay, so I'd like to talk about the origin, or what we think the origin of this remarkable world is. Alan mentioned and emphasized just how unique and strange the shape of Ultima Thule is, but there's something even more amazing about it. If we actually, these are the 2 lobes of Ultima and Thule, as we call them. They're not spheres like we thought back at the very beginning of the encounter, but they're actually these 3-dimensional bodies, and so that means they have axes. Long axis, a short axis. These are sort of the principal axis of the body, an intermediate axis. And when you actually use the shape models, you actually find out that these axes are remarkably well aligned, certainly to within 10 degrees of one another, and probably even better than that as our shape models evolve. So this is almost certainly not something, it's very, very improbable that this would arise completely by chance. And what it's telling us, the implication is that these bodies almost certainly were in orbit around one another, as Alan mentioned earlier. And when they're close, their mutual tides, their mutual gravity causes this alignment. It's a natural outcome of the tides. And then, as we've also said earlier, at some point, due to some process, which I'll talk about in a second, they're able to merge and then stick on their long axis. I mean, back at the time of the encounter, we talked about the snowman, right? You're thinking of 2 big spheres. 2 spheres can stick to each other in any direction, and it doesn't make any difference. But these 2 lobes are stuck together in a very specific way. Just like Alan was saying, I mean, you could imagine a meatball on top of a pancake. Well, that's not what this thing looks like. It's like stuck end to end. And so we've really, I think, finally gotten really hard evidence of, sort of an initial configuration of this binary planetesimal. Now, of course, even more, at least as intriguing, I should say, are the individual shapes of the bodies. Ultima, in particular, the Ultima lobe, is very flat. It's, if not the flattest solid body we've seen in the solar system, it's certainly up there. And we look across the solar system for possible explanations for this sort of flatness or analogs. And 2 that pop out are in fact some of the smaller satellites of Saturn. These are not all to scale here, but they're very different. So if you look on the right, there's a moon called Hyperion. It orbits quite a distance from Saturn. It is intensely cratered, far more intensely cratered than Ultima or Thule, and it's been battered and chipped away, and it sort of looks like a hamburger now. We don't think this is a very good analog for what, or a good explanation for the flatness of Ultima. Now at the other end, there's a moon there called Atlas, and it has a friend named Pan. They both orbit in or among the rings of Saturn, and what they've done is they've accreted skirts of very fine icy particles that you can sort of see in this image. Now when I first looked at these images, I said, well, this isn't like Ultima either. But the more we've thought about it, this is an accretionary environment. This satellite is accreting particles. The particles just happen to be small. I mean, there might actually be some link here to how the components or units, if you like, of Ultima actually came together if they were all in some sort of plane. And it's sort of the monkey bread analogy that Kirby was talking about. But we still don't know the answer, and we're still working on it, and what it really requires is some detailed modeling. So it is indeed a work in progress. When we step back, though, what Ultima Thule is teaching us is that the formation of a binary that first forms as a co-orbiting pair and then merges fits in with one major class of theory for how our entire solar system formed. If you go back to the days of the solar nebula, the gas and dust that's circling the sun, there are modern theories which postulate that there are overdense particle, or sometimes called pebble concentrations, that then can gravitationally merge together. That is, large swarms that could form relatively large bodies of the scale of Ultima Thule or even larger. Now, they don't just form and fall into the center and go poof. There's always a sense of spin or a sense of swirl or angular momentum, to be technical. And so as these particles come back down together, they will naturally form binaries. And this can be demonstrated theoretically in computer models, and this has actually been done. So what we actually think is that these collapsing particle or pebble clouds make binaries that are still associated with maybe even other satellites or just nearby objects. And so there's going to be further angular momentum or spin transfer, either through tides through these third bodies, or there's got to be some effect from anything that collides with the two bodies. It'll change their angular momentum state. And there may even be some residual effect of the solar nebula gas, which is, slowly dissipating in the earliest days of the solar system. Again, we don't know exactly what combination of these processes allowed the two lobes of Ultima and Thule to merge, but we are now confident that this is actually what happened, so that when we look at Ultima Thule today, it sort of looks more like this. And these beautiful graphics are drawings from our team collaborator, James Tuttle-Keene. So what I'd like to do, though, is illustrate one of the things that we can actually model and have modeled recently, and that's the work of another team collaborator, Derek Richardson, and his team, including Julian Marhonik. And what they're doing is actually looking at the end product, the end merger of two lobes. And I'll just show it to you. So this is what's called an N-body simulation. And over several 100,000 individual particles. This is a slow merger, just like Kirby said. This is two bodies that are coming together. They're very weak. They have very low gravity and low density, and they're the size of Ultima and Thule. And they're colliding at a speed of 2 meters a second, which is, if you take a brisk walk into a wall, you'll find out what that's like. But I don't recommend you do that. The movie you just saw, everything is blue. That's not the actual color. It's not like the color interpretation we've just been talking about. The blue and the red reflect the maximum acceleration that the particles have experienced during this merger. So you see that most of the distortion and activity is occurring in the neck region, which of course makes a lot of sense. So this is the kind of situation we think actually is the end game for Ultima and Thule. And of course these are spheres, and of course we'll be doing this for much more realistic shapes in the future. So I'll just sum up by saying, what has it been teaching us? We do now, just like Alan said, there are many primitive bodies in the solar system, but we have now reached the point where we can look at something which is truly pristine as you can imagine it to be. We are looking back to the very earliest epoch of planetesimal formation, planetesimals being the building blocks of planets. We've heard these lobes are similar in color and in composition, but they obviously are different in shape, and maybe they're even different in assembly, and that's something we're working on. And as I've given the evidence that we think it's a gentle merger of the two lobes at no more than a few meters a second. The lobes are aligned by their mutual gravity before they merge. And it's consistent with a major and important class of theory for the formation of planetesimals in our solar system. And I just have to say, I think without exaggeration, the targeting, The arrival, the encounter, the exploration of MU-69, Ultima Thule, it's been a breakthrough for our understanding of how planetesimals and indeed how planets formed in our solar system. And I'll also say, I don't think this just applies to some remote region of the Kuiper Belt. I think it applies through the entire solar system. And with that, I will hand it back to you, Alan.
Mike?
Before we take questions, I'll point out that all the graphics that the team is showing, they are available online. So they're on the New Horizons website, pluto.jhuapl.edu. There should also be a link to all of those graphics on nasa.gov as well, but they're available. So what we'll do is take questions. Now we have the microphone here. Maybe if when you guys get the question, maybe repeat a little bit part of it into the microphones for the web audience. So Emily, start.
So I guess this is probably for Bill, fairly speculative question.
Okay.
Doing that. How would you, now that you've seen a whole classical Kuiper Belt object, how do you think scattered disk objects are different?
I don't think they're fundamentally different, although the total amount of mass in the original, if you like, ancestral Kuiper Belt from this, that the scattered disk was created from, there might have been so many more bodies, there might have been a greater amount of collisional evolution with those. You know, the cold classical region of the Kuiper Belt is a kinder, gentler region of the solar system.
Yeah, Alex Woodsey with Nature. For Alan, could you talk a bit about future steps for New Horizons? If you were to write a proposal and get grants for future funding, how many candidate additional Kuiper Belt objects are you looking at right now, and what types of time frame and distances would you be looking at in visiting those?
Okay, so the question's what's next for New Horizons? I'll start by saying that we're currently funded through 30th of September 2021, so another 2.5 years almost. And it will take half that time until late next summer just to get all the data down from this flyby. And then next year, in 2020, we'll submit a proposal to NASA to make the next phase of exploration with New Horizons. To preface that, the spacecraft is very healthy. All of the onboard systems are working very well, and so are all of the backup systems. We're not relying on any backup systems now. The spacecraft has plenty of power from its nuclear power generator. In fact, we can run it into the mid-2030s, maybe later than that. And we also have a fair amount of fuel on board. We have more fuel on board, just a little bit more than it took to target this flyby back in 2015. So, as you may know, we already used the spacecraft to study the Kuiper Belt environment with our radiation and dust sensors, and we used the LORRI telescope and camera to look at dozens of other Kuiper Belt objects for contextual studies, objects that we don't pass close enough to resolve, like this wonderful object, Ultima Thule. And we would plan to propose to do both of those things in the next extended mission. And also, we would like to have another flyby of a Kuiper Belt object even farther out. That's going to be challenging because as we get farther and farther out, the objects are fainter and fainter as seen from the Earth. And you may know, Alex, you probably do know, it took us 5 years of searching from the ground. That came to precisely 0 targets that we could reach. We had to go to the Hubble and work at the limit of the Hubble's capabilities to find Ultima Thule. So objects even farther out will be even more challenging. And unfortunately, the really large telescopes that are being built for the 2020s, these 25 and 30 meter class telescopes, are not yet online to help us. So we think that the search for a next target will have to be made in a really innovative way with the LORRI camera on board, that we'll have to search by taking our own images of objects that are relatively close to us. And as an example of that, you know, we acquired Ultima Thule at the beginning of that video that we showed back in August from more than 100 million miles away. So we can see these things several months in advance, and if we can find targets that are going to pass near our path of flight, near enough that within our remaining fuel supply we can get to it in those few months, then if we have also pre-prepared what we call a shelf build of software to execute that flyby, then the combination of those two things would allow us to get another flyby. We probably only have the fuel for one. In fact, we may have to be very lucky to even get that one, because as we go farther and deeper in the Kuiper Belt, some models indicate that the population steeply drops off. If it does, that might prevent us from being able to get something we can get to. But if it doesn't, then our odds will be much better. We'll be in the Kuiper Belt until the late 2020s, so we have almost a decade to search and hopefully to find something. And if we do, you can bet your bottom dollar that exploring it will be another chapter in understanding the origin of our solar system, because by the time that we reach anything like that, we will be much greater distances from the sun, and so we'll be probing the accretion conditions, not 4 billion miles from the sun, but probably 5 or 6 or 7 billion miles from the sun. That was a long-winded answer, but there's a lot there.
At the speed you're going, how long before you reach the Oort cloud?
So the question was, how long until we reach the Oort cloud? The Oort cloud, for those who don't know the jargon, is a spherical assemblage of small bodies that were not formed where they are, but were ejected by the giant planets to the very farthest reaches of the sun's gravitational domain. And there's a bit of controversy about where the closest part of the Oort cloud is, the so-called inner Oort cloud. And it ranges from 10 times to 100 times as far away as the outer edge of the Kuiper Belt. So we'll reach the outer edge of the Kuiper Belt about 20 years after launch, and that would mean that the spacecraft would need between 200 and 2,000 years to get to the Oort cloud. And so that's going to happen. The spacecraft's going to reach it, but it's going to be derelict at that point, and all of us will be faint memories. Yes, exactly.
Someone else's vision.
Yeah, the electricity will run out.
Hi, Jeff out, Space News. Brown, you mentioned it's not until next September you get all the data back. Is there anything you're looking forward to in the near future in terms of the types of data you're getting back, or is that being prioritized by the initial results we have so far?
We are replanning as we go, and that's a process that John Spencer, who's sitting behind you, can tell you a lot more about because he leads it. There are two things that I'm particularly looking forward to, and others may have their own opinions. But first, we're going to get more approach images, and that's going to help us refine the rotation period and also give us more data to feed into the shape models. And then we're going to be getting back a lot more images of the sky around Ultima Thule to search for small satellites. And so far, we haven't found any, but there's a lot of data still on the spacecraft. And you know, the fact that Ultima and Thule used to orbit one another could mean, particularly because of the way that they would be drawn together by ejecting other satellites, that there might be a few small things left in orbit, that it wasn't a complete process in which these inanimate satellites back in the primordial days were ejected. It might be that there are a few remnants of that are left, and it would be very exciting to find out that that's the case. And it could also help us determine the density of the pair, the binary pair, by tracking the orbit of any satellites that we find. And we really don't have another way to get the density other than to make that find. Anybody else?
We're going to get slightly better, well, more phase coverage in the color. So that'll help fill in some of the gaps with, we don't think that there's changing in color as you look at the object at different angles, but that will enable us to fill in some of the gaps that we have. Not many of the gaps. The approach phase coverage was very stable, but every little bit helps.
Well, I was just going through, I have one other tidbit, that something I'm looking forward to is we'll have, you've seen the approach images at fairly low phase and then the thin crescent image. We actually have an image we took right at closest approach. And that's still on the spacecraft. It's massively smeared because we were scanning back to begin our next scan in one direction. The object was moving in the other direction. We were reading out in the wrong direction. It was the only way we could read it. it could be so blurred we see nothing in it. But if we do see something, it's going to give us a unique view, pretty much broadside on of this object. We'll have that down in the next month or so. Looking forward to that.
Excellent.
Capture all that.
I have a question for Carly and Sylvia. So far, you talked a little bit about how you saw some areas are bluer, some areas are redder, so that's just slope. Have you seen any evidence for absorption features that are different from one place to another on the other?
This is a you question.
Okay. We looked for it. We see subtle differences, but we are not ready to comment yet. We need to work very hard to look for differences in strength or shape of the absorptions.
If I could actually follow up, I was looking at your LISA image, and correct me if I'm wrong, but it seemed to be brightest in different places from where the Lori image is brightest.
Yes, that's correct, and there could be differences in whether it's a difference between the brightness of the overall object, you know, like to be more specific, like the radiance factor could be higher or lower, or the albedo could be higher or lower in different regions. So for example, in the visible wavelength range, the neck seems brighter. But in LISA, you are seeing the contribution of several factors, including the strength, for example, of methanol, which could lead to a region being brighter than the other.
Thank you.
But hopefully we will have results in that respect soon.
There we go. Okay.
Hi, Lisa Grossman from Science News. I was wondering, is Ultima Thule considered a planetesimal in its own right, or just the things that clump together to make it? And then, Bill, you said this was a breakthrough in our understanding of how planetesimals form. In what sense is it? What is the breakthrough, given that so much of this is still speculative?
Well, okay, so I'll back up a little bit. So the sort of back when I was a graduate student kind of thing. You know, a simple idea about how planetesimals that build planets form is that just, you know, small particles stick to other small particles, they get bigger, they slowly get bigger, and bigger particles stick to and make bigger particles, and it goes on up in a sort of ladder. That's sort of the traditional view, but the kind of more recent theoretical developments have really emphasized aerodynamic effects in the solar nebula, which bring large numbers of smaller particles together at once, which then can, by gravity, form all at once relatively large bodies. Now, I'm not talking 100 meters, I'm talking about things the size of Ultima Thule, things the size of small asteroids and so forth. And the evidence we have from Ultima Thule is that this fits in with this picture and not with the other one. In fact, it was even a puzzle to even understand how bodies would form in the cold classical Kuiper belt, because there's so little mass there, so that in a traditional hierarchical coagulation model, as it would be called, you would never be able to do it out there. And so other theorists have tried to imagine ways you could actually transport bodies from closer into the sun and deposit them in the cold classical region. The problem being is that the cold classical bodies are redder, and they have a different size frequency distribution in terms of their sizes, and a very large binary fraction, none of which, certainly the latter is not consistent with this sort of large-scale dynamical scrambling. So, but this other gravitational instability model, this aerodynamic model, sometimes people call it the streaming instability or goes by other names, actually will work with low amounts of mass. And we think we see the end product right there. And so when I say this is applicable across the solar system, I'm not saying everything should be as red or have the same chemical composition as Ultima Thule, because you have different compositions in different parts of the solar system depending on how close to the sun you are. But the dynamics probably really do work this way.
And Lisa, if I can add to that a little bit, you know, the way that science works is that the modelers are doing their best to put all the physics in that they think is important, but different models are indistinguishable from, well, they were before this flyby, indistinguishable from the data that we had. And now by seeing this particular object, and we've been able to see which branch we should be on of all these different models. And so that's a huge step forward. And you know, even within the bifurcation that Bill was talking about between the hierarchical accretion models and the streaming instability pebble cloud collapse branch, even within the latter, which we now think we have strong evidence for, there are different offshoots of that. And the fact that we can see that this object had to have merged gently, and you know, and then we think about how that merger could have taken place, it's telling us that either there was gas around, as Bill said, that was dissipative, or there were lots of other things orbiting with the Ultima and Thule before they merged, and that it was their ejection that resulted in the orbit shrinkage to ultimate merger. Or it may have been both, but these are all important forensic clues from a time 4.5 billion years ago that we didn't have until the 1st of January this year. So it's really propelling the whole field forward now, because some models are fallen out of fashion because the data just doesn't support them anymore, and other models are going to get a lot more attention now to try to explain exactly how this object with this unusual shape and alignment of the lobes came together.
Yeah, and I should probably add one more thing, because I didn't quite answer your very first thing you asked me. So both lobes, when they were individual, we would consider planetesimals, but when they merge, it's still of this small enough scale that it's a bigger planetesimals. At some point, if we get to call them protoplanets, what exactly that scale is, I'm not sure.
Just to clarify from Lisa's question, so the idea is because the Ultima sort of flat pancakeness of it, that's what supports this kind of streaming stability model?
It's the binary nature and the fact that the alignment is required. It's almost certainly requires a kind of tidal effect to. Yeah, they're stuck together in a very specific way, which comes right out of these streaming instability style models. And in the other kind of model, it would just be anything. Things would just bang into one another. And as Alan mentioned a little bit earlier, at definitely higher speeds. And you would expect entirely different kind of geometries.
I can change your times. There were things you looked for I didn't see, like in the atmosphere, and you didn't expect to see them. I was wondering if there's anything you didn't see that you're surprised by not seeing, especially composition-wise.
You want to talk about composition?
You can take the first.
Well, I'll lead. Sylvia's the composition expert here. Carly's our color expert. She can speak to that. But I'll speak to the fact that we didn't find satellites so far. And, you know, the cold classical population in the Kuiper Belt is known for having the highest binary fraction around anywhere in the Kuiper Belt. At least 30 or 35% of all of the known cold classicals have satellites. And it's probably a still higher fraction, because if the satellites are too small or if they're too close to the primary, we couldn't see them from the Earth. So those types of satellite systems, you know, have to be added to the 35%. We don't know how high that makes it go. So I thought it was a pretty good bet that we would find satellites. We think now that the reason that we haven't found satellites is related to this merger, as we were describing earlier, that the merger event required the dissipation of energy and angular momentum, in part through the ejection of former satellites that are nowhere to be seen now because they were long gone 4 billion years ago. And that surprised me.
Thinking about the color, perhaps it's not a surprise, but what I was hoping for was something akin to the red splotch that we see on Nix, right? It's something that had come in and impacted and perhaps revealed some of the subsurface. So maybe not a bright ray crater, but something that was kind of excavated the top surface so we could see a little bit further into it. And we know that there's not a lot of things floating around in that part of space to cause those sorts of impacts, but it's always worth hoping because you never know what you're going to see. So that's what I was hoping for that wasn't there, but I can't really say I'm truly disappointed because it's not that surprising.
So in terms of composition, given the size of the target, because it's very small, we were not expecting the presence of volatiles such as methane or nitrogen or carbon monoxide. A small part of me was hoping still to find them to, reject the current models, but
Always a good idea.
we didn't find any clear evidence of such volatiles. I didn't mention in my talk, in my presentation, we find an absorption feature at 1.8 micron, which we do not know the species responsible for it. So these objects still leaves a lot of room for further exploration and for further understanding what is present on the surface of small objects in the third zone of the solar system.
Did you want to?
Personally, I didn't know whether we would or would not see ejecta deposits around craters. Bill's laughing. We do see ejecta deposits or ejecta blankets on around small craters on small bodies like Phobos and other smaller worlds too. Ejecta, stuff that gets tossed out of impact craters, some of that could still be below escape velocity. We didn't see anything definitive.
I suppose if I had to say something I was disappointed not to see more of, it would have been bona fide, absolutely unequivocal impact craters. But the real reason is not that they're necessarily not there, but because the shape of the ultima lobe is so flat and the subsolar point is right dead center that it kind of washes out the topography. So we lucked out in one way, in a more important way perhaps, by seeing the shape actually than in terms of finding impact craters. We have to really look along the sloping, the edge, to see the topography in general.
Mm-hmm.
I think we're right up against it, so why don't we close it out with the video?
Oh, yeah, we can do that. I don't know how we initiate the video over here. Just go to the next slide? Okay, so, all right, so as I said at the outset, we showed this approach video, which is really beautifully done, and again, it's John Spencer who led that effort. A bunch of people on the team participated in that, but John led it to put together this whole time lapse from August when we first spotted Ultima faintly against the star fields of Sagittarius until we actually flew up to it on New Year's Eve and New Year's Day. But back in 2015, Queen lead guitarist Brian May approached our team and wanted to join us scientifically, not as a musician, but scientifically. And most of you probably know that he actually earned his PhD in the 1990s in astrophysics. He had started it back in the 70s before Queen was the thing. He put it down for a long time, and then he wanted to finish his degree. He did, and has participated in planetary science and some astrophysics over the years since he earned his degree. So who was I to say, no, Brian, you're not going to be on our team? And he's actually contributed substantially. He, along with Paul Schenk, are our two stereo experts. So, but in addition, he's actually lent his musical talents to the public outreach part of New Horizons. And this summer I challenged him to write something around the flyby and the exploration we're doing, and he flatly turned me down and said, no, I can't write lyrics because nothing rhymes with Ultima Thule. But then he thought better of it and eventually created this anthem he calls New Horizons. And last week, he mixed excerpts of that anthem with the video that John Spencer and his team put together. And it's being released simultaneously today by NASA and by Queen and their PR machine. And we're quite proud of it. We think it's another first for New Horizons. And I guess I'm just gonna hit advance and you'll get to hear it. It's pretty cool. And it's quite short. Great, and you can link it to your social media. You can put it on your websites
You can use it
with
as a
the
ringtone.
articles. Yes, use it as a ringtone. That's even better. Thank you, Bill. All right, Mike.
have for it today?
It's playing again.
And that concludes this press conference on 2014 MU69, the roughly 20 mile across Kuiper Belt object that was recently visited by the New Horizons spacecraft, made of two components, one about 9 miles across, the other about 12 miles across. This strange shaped bilobate object is getting better and better understood with every kilobyte of data we ever so slowly are able to download from this spacecraft. Now, this particular press conference landed smack dab on top of our normal Daily Space episode. We are now going to switch over to bringing you today's news, delayed by this breaking news. So stand by. Things may slightly freeze as I switch over the settings. Here we go in Hello and welcome to today's Daily Space, brought to you after a bit of a delay from the live press conference for Ultima Thule 2014 MU69 from this week's big event, the Lunar and Planetary Sciences Conference down in the Woodlands, which is just outside of Houston, Texas. Now, for those of you who join us during our live events, we actually do something kind of, silly and fun and awesome, and that's play bingo. This was put together by our own Annie Wilson. Thank you so much, Binary Ablaze, for doing this. And I kind of got a bingo, but since I work here, I didn't think it was appropriate to press bingo, but I needed to tell you. And this is yet one more reason you should join us for live coverage of special events related to space. Not only do we answer your questions, provide a place for you to chat with other people about what's going on, but we also play really ridiculous games of bingo. Now, this is not why we are here. We are here to check on all that is new in space and astronomy. One moment, I need to turn off my water heater. There was a refill of hot tea that needed to occur during that press conference. Now, we have a variety of awesome stories for you today. The first one is one that didn't seem entirely space related until I really got down into reading the press release. This particular story details how scientists looked out at the trembling aspen trees that Colorado is so very famous for and started to think through what is it that causes the leaves of these trees to tremble and basically oscillate as much as they do under very low wind speeds. And once they got to thinking about that, they got to thinking about how might this be able to be used to generate electricity? And how might this be able to be used to generate electricity on Mars? One of the problems that we dealt with recently in the most sad way was the loss of the Opportunity rover. This little Mars exploration rover that had been on the moon for over a decade, had been on Mars for over a decade. This little rover so far exceeded all of our expectations. But it, in the end, gave its life in a dust storm. Because it was powered by solar electricity, it just couldn't recover from spending weeks beneath completely opaque skies. Now, what this research team looking at the trembling aspens thought, and this is a group from Warwick University in the United Kingdom, what this group got to thinking about was if they could figure out what it was that made aspen leaves so efficient at transforming wind into oscillations. If they could figure it out, they could build lightweight pseudo leaves, artificial leaves, I don't know what you want to call them, that through their trembling in the wind would be able to generate electricity that in the darkest night could continue to power these little rovers. So sometimes a brilliant idea comes from when an apple drops out of a tree, and sometimes it comes from looking up and going, why are those leaves oscillating? And the answer to that particular question happens to be the aspen leaves are super flat, and even their stems are flat. So from having this flat stem, flat leaf, they are able to better capture and oscillate in the wind. Things you learn every day. Okay, so going on to our next story. This is something I kind of hinted at in the Twitter tweet leading up to this show, and I had to say embargoed cratered Turkey, or hit Turkey, I think is what I said. And this is because this story just came out of embargo. There was, not too long ago, a impact in Turkey of it was a 1 meter asteroid bit that decided it was going to come in. It was going to shatter at an altitude of about 27 kilometers. That's about 17, 18 miles. And then all of the bits of this shattered tiny asteroid rained down on the Turkish village of Sarıçak. Now, it was a real boon for the locals. The villagers went out, they gathered pieces, they sold them. It was revenue that literally fell from the skies. I want to say this again. Money fell from the skies as far as these villagers were concerned. And they were able to go figure out where all the pieces landed thanks to security cam and dash cam and other, closed circuit television devices. So here you see people out searching the fields, one child holding up a fairly large chunk. Now, because we were able to see this object fall out of the sky, which meant we could backtrack and figure out its velocity through space, because we were able to gather samples up of this rock, it suddenly became possible for people to figure out the dynamics of the orbit of the object and to then measure the chemistry of the meteorite and its parent object. And what they were able to figure out was this is a false color. This is not real color. This is false color image where each color is representing the different minerals that are there. This is a false color image showing the mineralogy of Vesta. And this, in particular, the upper crater in this image is the crater Antonia. And it is now understood that these people in Turkey were attacked by Vesta. And it was pieces of Vesta that originated in Antonia crater that struck this world. Now, what this means is the scientists were able to say, okay, this chemistry matches. Let's look at the dynamics of this. And from the dynamics, they were able to figure out this probably rained down from this area. And another thing from the chemistry is they were able to figure out how long it had been in space. And it was about 22 million years. And this particular crater matches the chemistry, matches the dynamics, and formed about 22 million years ago. So this is one heck of an excellent piece of sleuthing that is brought to us by the good folks at the SETI Institute. You may remember this is the same institution that went out and looked at the asteroid that rained down over Botswana, not last summer, but the summer before, and were able to similarly figure out where the fragments of meteor landed and trace it back through its dynamics. So this is a new thing that, thanks to having cameras everywhere, we are able to scientifically benefit from. Now, moving on to today's final story, and this is something that you're going to be hearing more and more from us about. Alexis Rodriguez at the Planetary Science Institute is basically studying shorelines on Mars. So if 3.4 billion years ago you had decided to go on vacation on Mars, well, first of all, you wouldn't have existed, because really there wasn't life really of any significance here on Earth at that point. But should your little microbial self have decided you wanted to go on vacation to Mars, you could have visited the seashore. And it wasn't just one large ocean at this point in time. There were also various runoff basins. There were inland seas like the Dead Sea that we see today, as well as the Caspian Red Sea. There's all these little inland seas scattered throughout our planet. And Mars had them too back then. And it's now turning out, as we study more and more and begin to understand more and more of what we're looking at from the high resolution images and chemistry that we're learning about with the red planet, it's now understood that back in 1995, I believe it was, the Pathfinder mission, when it landed on Mars, it was landing actually on the seashore. So we've already sent a spacecraft to explore the seashore area of Mars. So we can't say that she sold seashells by the seashore, but we can say Pathfinder, I don't know, I can't make the words rhyme, but Pathfinder saw rocks on the seashore of Mars. So this is cool, and this is just the beginning. There is so much under embargo that I can't tell you, but I can tell you to just keep coming back, and we'll be able to tell you more and more of what's going on this story. And we will probably have Alexis on at some point in the future. And that concludes all the news for the Daily Space today, March 18th, 2019. I will now take your questions. Please at me in the chat to make your questions easier to find. And while you are typing them in, I'm just going to remind you that the Daily Space is part of CosmoQuest. We are here not just to bring you this show, which we do most Mondays through Fridays at 1 p.m. Eastern. That is 10 a.m. Pacific, and right now that's 5 p.m. London time, because not everyone is on daylight savings time. We are a production of the Planetary Science Institute, working in collaboration with Youngstown State University. We bring you the Daily Space, we bring you Sunday Science Hour, and we, of course, as we did today, bring you breaking news as it happens live right here on this channel. So give us a follow to find out when we're going live. Follows are free. Thank you, Kabarut, for the follow. Or the sub, rather. I'm raining bits on the heads of my dogs who are very sleepy. Cheers. Thank you. Thank you, Mythtown, for subscribing with Twitch Prime. Here, go over there. Go. And we also have a tradition that we make it rain Cheerios for the dogs when bits come into our channel. So thank you, guys. Thank you. You all are so wonderful. Cheers to you. I am now going to take a look at what questions you have for today. Let's see. Veronica Cure proposes Pathfinder shared shore rocks from shoreline on Mars, from the shoreline on Mars. We're getting there. We're getting there. Yes, Arnstro, feed the wiggle butts. I have one wiggle butt and I have one wagtail. Stella has a tiny, tiny, ridiculously tiny tail. Okay, so let's see what else we have in the chat. I'm scrolling up to see what all I can find. Yes, Arnstro, bingo. Let's see what else. Yeah, R.I.P. Opie, he is messed. Yes, Vesta attacked Turkey. It is true, and it is a new awesome thing to understand. Arnstro, that's great. Asia Minor, let me say that again. I can't say that. Asia Minor attacked by Vesta. News at 1800. How's that? I'm learning there's certain words that I really struggle with. Red. Red is one of those words that unless I really think about it, I can't say. I did not know this about myself. 6,355 meters is 6 kilometers, which is 4 miles. That would be amazing, Larry, weird and proud. I would love to specially breed flowering succulents for Mars. So disillusioned, embargo means that the information exists, but we're not allowed to share it. And so an embargo may apply to information that I receive as a member of the press. So I have it and I'm allowed to start working on a story and contact the scientists. So the story that I presented from the SETI Institute about the meteorites striking in Turkey, I had that under a press embargo. The work that Alexis Rodriguez is doing, I'm helping him figure out a few different things that aren't so much science related, but I know about it because we work at the same institution. And so that's under a colleague-to-colleague embargo. And then, of course, collaborators know things first, know things before they're understood. And that's just a don't tell anyone collaboration kind of embargo. So there's lots of different ways you can end up with information. And then, of course, there's the two scientists drunk embargo of, he probably wasn't supposed to tell me that. So I'm not going to talk about it. I don't actually have any embargoed information like that right now. But good humans don't give away things they're told when the scientist they're talking to is drunk, because that happens. This is why I don't think we've actually discovered aliens, because somebody would have said something in a moment of stupidity. Okay. There we go. That seems to be the end of today's questions. Now, I, for one, am dying for lunch. I don't think you can fully appreciate the look Eddie is giving me. Let me see if I can zoom in on the look. This is the look of a dog that would like to go through the door, or at least have more Cheerios. So I think it is time to wind up today's episode. Thank you all so much for being here. I will be rolling the credits and finding someone to raid. So thank you for being here once again. Thank you, Veronica. There you go. There you go. He is so excited. Stella's like, yeah, I'm just going to sleep. Thank you so much, Veronica. So stick around. We will find someone to raid. Thank you, our Instro. Let's see if Stella is Whoa, I just put my hands in my tea instead of in the Cheerios. There, go. Stella is considering maybe moving. So thank you all for being here. Thank you for everything that you do, supporting us. We are a production of the Planetary Science Institute, working in collaboration with Youngstown State University. We are here to put science in your brain, and with CosmoQuest, we invite you to not just learn science, but to also help us do it. While our citizen science sites are down right now, hold on and stick with us, because in the coming months, we will be helping the OSIRIS-REx mission find that rock that they're going to bring home to Earth. And we're going to be working to map out this little world with new and amazing images. So the best is yet to come, and is yet to come thanks to you. We are supported through the generous contributions, donations, bits, and subs of individuals like you. Thank you so much for supporting us and supporting us keeping the science going. So, wherever you are in the world, have a fabulous morning, evening, afternoon. And if the weather allows, go outside and look up. Thanks for being here, and bye-bye.